So in today's video, I'm going to be looking at 10.3 and 8.5. 10.3 is very similar to what we just covered in 10.2, where we looked at confidence intervals for the population mean. I'm going to be doing the same thing here, but looking at confidence intervals for the population proportion. 8.5 takes us way back to what we did before all this central limit theorem stuff and looking at confidence intervals. It takes us way back to what I should have done before spring break and just didn't get a chance to do that. So I will cover that in this video. But first, let's start with 10.3. What we're trying to do here is we are trying to find a confidence interval where I am a certain percent confident that my population proportion that I'm looking at will lie within this range. It will lie within this interval with a certain level of confidence. Okay. First of all, taking us back, I very quickly want to mention this. If you want a point estimator for your population proportion, okay, so we're trying to find a way that we can estimate our population proportion. Two ways we can do it, either by using a single value or by finding an interval that it will lie in. The first thing we will do is for a point estimator for the population proportion. Okay, remember we call that P. Okay, a good point estimator, a good value that we can use to estimate our population proportion is the sample proportion, where I have taken a representative sample and I look at what proportion of people or things in that sample have that certain characteristic that I am looking for. And whatever proportion of people in my sample have that characteristic, I can use that as an estimate for how many people in my population will have that same characteristic. So a point estimator for the population proportion, P, is the sample proportion. P hat. Okay. We're going to use that again in a minute. We've also looked at this before. But now looking at my interval estimator. So I'm going to an interval that I want this interval to contain my population proportion. So an interval estimator for the population proportion. Okay. You may remember from when we covered this in chapter 9 that there is a Z transformation for the sample proportions, because our sample proportions, as long as there were certain properties that were fulfilled, our sample proportions could model a normal distribution. So they could take on this normal distribution as long as they satisfied, there were two properties, if you look back at 9.4, that they had to satisfy. When we do this, our Z transformation for our sample proportions was our sample proportion minus the population proportion over the standard deviation of the sample proportions. Remember that the population proportion was also the mean of my sample proportions. Okay, it was a good estimator for it. So we do our sample proportion minus the population proportion divided by the standard deviation of the sample proportions. Okay, plugging in our formula for our standard deviation of sample proportions was this formula here. So it was the square root of P times 1 minus P over N. Okay. Again, look back at 9.4. That's where we covered this. Just as a quick recap that I did mention in 9.4, sometimes you are not told what the population proportion is when you do this Z transformation. Okay. So occasionally, and we'll look at this in a second when we rearrange this stuff, occasionally you will have to, instead of using the population proportion in your standard deviation here, you may have to estimate that P using the sample proportion P hat, okay? You normally have sample data, you may not have the population data, okay? And we are trying to find a good estimate for this thing. So what I tend to do for my Z transformation is actually state it this way instead. P hat 1 minus P hat over N, okay? Where I have estimated my population proportion by my sample proportion instead, okay? Now, using this Z transformation, I want to find an interval estimator for my population proportion. So I'm going to use this formula to estimate this value, okay? Now, going back to what we just did in 10.2, you may remember that I said, we always said with our empirical rule that within 2 standard deviations of the mean, you should have 95% of your data. That means in our standard normal distribution, that between 2 and negative 2, okay, remember that 0 is the mean, standard deviation is 1. So therefore, in our standard normal distribution, 2 standard deviations either side of the mean takes us between 2 and negative 2. And between those values, we have approximately 95% of the data. Okay? And I said to you in 10.2 that in actual fact, it is 1.96 either side of the mean gives us exactly 95% of the data. Okay? Because we said that if we went 2 standard deviations either side of the mean, so if Z was between 2 and negative 2, the probability of landing in that range was approximately 0.95. Okay, there was a 95% chance approximately that we would land in that range. In actual fact, to get this thing to be exact, it's actually the probability that you land between negative 1.96 and 1.96 would give us exactly 0.95. Okay, so we can take that approximation out of it. Because that is true, what I'm going to do is plug some stuff in here. So I know that for my sample proportions, I can let Z, let me back up on that. So I can let Z, other way, there we go. I can let Z equal this thing. Hopefully I've got enough space to do this. Over N, okay, and that is less than or equal to 1.96, which is equal to 0.95, okay. I can rearrange this thing, so I can multiply up by this standard deviation term. So if I multiply both negative 1.96 and 1.96 by this standard deviation term, okay, I can then subtract my sample proportion all the way through. So I can subtract it from what term I would get here and subtract it from the term I would get here. And then I would have to multiply all the way through by negative 1, which will switch around my inequality. Whenever you multiply by a negative or divide by a negative, it always switches the inequalities, okay? And that will leave me with my population proportion in the middle and bounds on either side. When you do that, what you should actually get, when you go ahead and figure this out, you should get P hat minus 1.96 times this standard deviation of the sample proportions here. I'm going to shorthand that whole thing right now just so I have enough space. But all I am looking at here, when I talk about the standard deviation of the sample proportions, it was this term here. Okay, so I'm going to shorthand that right now to just be sigma of P hat is less than or equal to P, which is less than or equal to P hat plus 1.96 times that standard deviation term is equal to 0.95. Okay, so I know that I now have bounds on my population proportion. It can be as small as this value or as large as this value with a 95% certainty that it would land in that range. So I am 95% certain that my population proportion will land between this value and this value. Okay. Again, I'm going to now extend that to be however confident I want to be. In this case, we were 95% confident because we were looking at a 0.95 probability. So I was 95% confident here that my population proportion landed in that range. What I now want to do is extend that to be any percentage of confident that my population proportion will land in some specific range. So again, I'm going to write this all out, and it may look kind of weird right now. It's got very much the same setup as what our population mean had in the last section. But what we now have is if the sample size is sufficiently large, so remember for the population mean and sample means that we had last time, we had to have the n was at least 30. In this case, we have our two other properties that we have to satisfy for the sample size to be large enough. So if the sample size is sufficiently large, okay, if you go back in your notes for this, you'll know that that means that our sample size times our population proportion should be at least 10, and our sample size times 1 minus p has to be at least 10. That means that I have a large enough sample size, okay? And remember, this is kind of weird notation, but I want to keep with what we have all the way along. This confidence level that you have, so in this case you could be ones that we've looked at so far is like 80% confident, 90% confident, 95% confident, etc. You can write it like this, just be aware of that. But again, I'm going to draw this all out for you guys so that you can see it rather than using this weird notation. But the confidence interval for the population proportion P is given by P hat plus or minus some z value times the standard deviation of sample proportions. That can also be written as that z value and our standard deviation of sample proportions. Because we do not know our population proportion right now, we're trying to find an interval that it lies in. We only know our sample proportion. So I said when we do this, we are going to use that sample proportion within my definition of the standard deviation of sample proportions, just as an estimate, okay? So I can rewrite this as this, okay? And if you wanted to write it in interval notation, it would look like this. Okay, again, remember when you are looking for that z value, okay, we had the z value for the last one where we were 95% confident we already know that that z value is 1.96. I just used that as an example. But if you do need to find that z value, we denote it as z alpha over 2 just as a notational thing. But if you ever need to find that z value, it's exactly the same as what we did in 10.2. So let's say you want to be 80% confident that your population proportion will lie within this interval. Okay, so quick example, if you're 80% confident, so you want an 80% confidence interval, okay, and you want to find that z value, go ahead and draw it out. Every time you do this, draw it out, okay? You know that you want to be 80% confident. So take that area to be 0.8. That would mean that 80% of your data is going to lie between z of alpha over 2, and negative z of alpha over 2, with 0 in the middle. 0 is the mean. We are looking at a z value here. We are in standard normal right now, okay? We want to be 80% confident. So we've got 80% of our data is going to lie between z of alpha over 2 and negative z of alpha over 2. You want to find this value, okay? This value here is only the negative of this value, okay? And we want to find it. We know because this thing is symmetric and because I've got 0.8 in the middle, I should have, with an area of 1 under the curve, I should have 0.1 either side. So if I now want to find that z value, I always tend to find the negative of it just to make it easier. I know that to find that, I have to use inverse norm in my calculator. My area under the curve to the left of that value, remember to always plug in the area to the left, is 0.1. My mean is 0, standard deviation of 1, because I'm looking for a z-score. I am looking for a z value. This thing here would give me negative z of alpha over 2, okay? So to find z of alpha over 2, just make that thing positive, okay? So whatever value you get, it should be negative. Just make it positive. It's just way easier to deal with, okay? So it's exactly the same. When you need to find that z-score here, it's exactly the same as what we did last time in 10.2, okay? As always, you do not have to do this by hand, okay? There is a function on your calculator that will calculate this interval for you. So if you go to stat, go across to tests, okay? This is exactly where we found all the z intervals and t intervals from 10.2, okay? If you go down, there should be on my calculator, it's option A, okay? So you've gone to stat, you've gone to tests, and you scroll down. Option A on mine is 1 proportion z interval, okay? So you want option A, 1 proportion z interval. Click that, and it will ask you for some information, and we are going to do an example so that you can see this. It asks for x, n, and the confidence level, okay? X is just the number of things in your sample that have that certain characteristic. It doesn't actually ask you for the proportion. It's actually going to find the proportion for you. So X is just the number of things in your sample that have the characteristic that you are looking for. N is the number of things in the whole sample. So X is the number of things in the sample with the characteristic. N is the number of things in the sample. So you should find with the notation that you have in your calculator, so if X is number of things in the sample with the characteristic, whatever characteristic that may be in the problem, N is just the sample size, okay? That means that your sample proportion, the proportion of things in your sample that have the certain characteristic, is just X over N, okay? So all you have to do is type in what X is and what N is, and it's going to calculate that sample proportion for you. You don't even need to do that. So you're going to have X, you're going to have N, and then you type in the confidence level. So whatever level of confidence you want to be that your population proportion will land within this interval, that's what you type there. Remember to always put your confidence level as a decimal. Do not put it as a whole number, okay? It always goes in as a decimal. So if you're 95% confident, you want to put in 0.95. And this thing will calculate that whole interval down here for you, okay? So you don't even have to work it out. It will calculate all the standard deviations, the sample proportions, everything for you. So now let's look at this example. This is from the practice on your homework, and a lot of these problems are very similar. So it says that an environmentalist wants to find out the fraction of oil tankers that have spills each month. I've gone straight to step 2 of 2. Step 1 is just where they ask you to find the sample proportion. So it's just going to be the number of things with the characteristic divided by the number of things in the sample size. That's all step one is each time they do this. So in this case, it says that suppose a sample of 399 tankers is drawn. Of those ships, 296 do not have spills. Using the data, construct the 95% confidence interval for the population proportion of oil tankers that have spills each month. Okay. Now, it's wanting the confidence interval for the population proportion of the tankers that do have spills. They have told you how many do not have spills, okay? So make sure you read the question in these, okay? So for part one, when it is asking what that sample proportion is of the tankers that do have spills, okay? The number that do have spills is just going to be 399 minus the number that don't have spills. Okay, so you've taken the number that there are in total, the 399, minus the number that do not have spills. Okay, so that tells us that 103 do have spills, 296 do not have spills out of the total of 399. Okay, so my sample proportion in part one would have been 103 divided by the 399. So we have a 0.258 sample proportion. Okay. So it says, construct the 95% confidence interval for the population proportion. So we want to find the confidence interval. We want to find this interval where we are 95% confident that the population proportion of all the oil tankers will fall within this range. Okay. So let's go to Stat, Tests, and scroll down to option A, which is 1 proportion Z interval. Now, X is the number of things that have the characteristic within the sample. So the number of things in the sample that do have spills, we said was 103. Okay. The number of things in your whole sample is 399, so N is 399. And the confidence level is 0.95. Okay, and we go ahead and calculate. So on my calculator for this particular problem, I get that my confidence interval is this. So this tells me that I am 95% confident that my population proportion P of the number of oil tankers that do have spills out of my whole population, the proportion of those out of my whole population that do have spills, must land within this range with a 95% level of confidence that that is the case. Okay. So the next thing that I want to look at is when they ask you for the sample size. Okay, so they have given you maybe the error and they've told you something about an estimated population proportion, or they have given you a sample proportion and they ask you what the sample size would be. Okay, now if you remember back again to what we did in 10.2 when they asked you for that sample size, I'm going to come back to my formula here. Okay, this is what we're going to be using. And we said that the error, when they give you what the maximum error allowed is, the error term is just this part here. Okay, it's the maximum amount that my population proportion and my sample proportion can differ by. Okay, so it's the maximum error between what my population proportion could be and what my sample proportion is here. So my population proportion can be at most this amount away from what my sample proportion was. Okay, so this term here is my error term E. So whenever they give you an error term, that's what they are referring to. So I know, if we come back over here, I know that my error term is that Z term, Z of alpha over 2, multiplied by my standard deviation of sample proportions. Now, there is two different ways that you have to bear in mind that you can do this, okay? If they give you an estimate for the population proportion, okay, that basically never happens. But if they say that the population proportion is estimated to be this, go ahead and plug in that value for P as your population proportion, and you can use that for your standard deviation of sample proportions. However, if they do not give you an estimated value for your population proportions, you will have to use a sample proportion as an estimate for it. So you can also estimate that error exactly as we have done when we have looked at these confidence intervals. You may have to estimate that population proportion by the sample proportion that may be given. Okay, you may have to figure out what that sample proportion is, that's fine, but just bear that in mind. So if they give you an estimated value for the population proportion, you can use that. If they don't, then this is what they are referring to. You will have to use that sample proportion as an estimate for the population proportion term. Okay, so I'm going to use this formula and I'm going to rearrange it so that I can find a formula for my sample size n. Okay, I'm going to use this formula here for this for now, but wherever you see a P, you can always estimate that by P hat, that sample proportion. It's going to be the same either way. Okay, so I want to solve for this term here. So the first thing that I am going to do is I am going to do a division by z of alpha over 2. So I'm going to divide both sides of this and this by z of alpha over 2. That's going to give me e divided by z of alpha over 2 is equal to the square root of p times 1 minus p over n. Okay. Then you can square both sides to give you e squared over z of alpha over 2 squared, okay, is equal to p times 1 minus p over n. Then you're going to have to do some cross multiplication here. So I am going to multiply both sides through by n, and I'm going to multiply both sides through by z of alpha over 2 squared. What that should give you is basically eradicating the fractions in this, and it should just give you something that all lies in a line. So multiplying by n on both sides and then multiplying by z of alpha over 2 squared on both sides should give you, you can do this in 2 steps if you want, that is totally fine. That should give you that, okay? Now I'm solving for n, so at this point, all I have to do is divide both sides through by e squared, and that will give you n is equal to z of alpha over 2 squared, p times 1 minus p divided by e squared, okay? So you square the z value. Then if you are given your population proportion or an estimate for it, you're going to do p times 1 minus p, and then you're going to divide by the maximum error allowed squared, okay? If, however, they give you the sample proportion, or you have to figure out the sample proportion sometimes, instead of an estimate for your population proportion, then that formula can be written like this instead. So either one of these works, okay? And you're going to find that z value in exactly the same way. They sometimes refer to it as a critical value. You find that z of alpha over 2 in the same way. You're going to square that value that you get for that z value. Then you multiply it by p times 1 minus p, or p hat times 1 minus p hat. And then you divide it by the maximum error squared, okay? Let's look at an example for this. So this says, the State Education Commission wants to estimate the fraction of 10th grade students that have reading skills at or below the 8th grade level. In an earlier study, the population proportion was estimated to be 0.22. So they have used previous data in order to estimate what their population proportion might be. So you can use that 0.22 as P. Then it says how large a sample would be required in order to estimate the fraction of 10th graders reading at or below the 8th grade level at the 80% confidence level with an error of at most 0.02. So we know that P is going to be estimated at 0.22. You know that the maximum error allowed is 0.02. And you know that you want to be 80% confident. So let's go back to our formula here. I'm going to write this formula out again. So we know that we have n is equal to z of alpha over 2 squared. They've given us an estimate for p. So I can use p. If they hadn't, we would have to use our sample proportion p hat to estimate instead over e squared. Now, the values that I was given, I want to be 80% confident. I'll do this in black. I want to be 80% confident. Okay. Then P was given as 0.22 and my maximum error that I'm allowed is 0.02. I would always write this stuff out and then you can plug it into a calculator. Please write this stuff out. Otherwise you will make mistakes when plugging this stuff in. Okay. The only thing that I don't have right now that I need to calculate is z of alpha over 2. So I know that I want to be 80% confident. So we're doing the same thing that we did before. You want to be 80% confident, which means that between z of alpha over 2 and negative z of alpha over 2, you've got an area of 0.8. That means that I have an area under the curve either side of these equal to 0.1. Okay. So to find z of alpha over 2, I'm actually going to find negative z of alpha over 2 first and then make it positive. Is inverse norm of 0.1, mean of 0, standard deviation of 1. So let me quickly type that into my calculator. I'm going to use inverse norm, an area of 0.1, mean of 0, standard deviation of 1, which gives me negative 1.2816 roughly. Okay, so that tells me that z of alpha over 2 is 1.2816. Okay, now I can go ahead and plug this stuff in. So n is equal to 1.2816 squared. P I've said is 0.22. 1 minus P, so 1 minus 0.22 would give me 0.78. And then divided by my error term, 0.02 squared. So I'll plug that all into a calculator. And I should get, this may take me a second, but bear with me while I plug this in just as you do. I get 704.63. Whenever you get one of these, always round up, okay? You always round up for sample sizes. So I get that n is equal to 705, okay? So all of your sample size ones should be exactly like this. Now, I discovered over, it was on Friday and then on Saturday morning, I put the sample size program on some of your calculators and it is also online. It is not working for some people. I am not sure why. The program does work on my calculator. I don't know if it transferred incorrectly when it got transferred over. So for some people it is working and for some people it is not. I will tell you how to do this for those of you that do have the program and it does work. But I know for some people it is just not working and I'm very sorry about that. We will just have to go about this the long way. You will be allowed the notes in front of you with the formula for your exams and stuff. I'm going to try my best to try and take this out of the exam, but I will update you on that a little later. But for now, I really want you to know how to do this the long way, just in case it does not work for you, okay? But for those of you where the shortcut does work, if you go to program and sample size again, if you go down to option 2 with one sample proportion, it will ask you for the proportion. So in this case, we know the proportion is 0.22. The margin of error is 0.02 and the confidence level is 80%, so 0.8. And it gives you that sample size of 705. So it is a much quicker way of doing it for those of you where it does work. I am very sorry for those of you where it doesn't work. We are just going to have to persevere with this online learning and do this the long way, okay? As I said, it is not bad. We have just done the example here, and all of the sample size problems are very, very similar to this. So now I'm going to move on to 8.5. 8.5 was what we were going to cover the Tuesday before spring break, but I didn't get a chance to cover it on that day, so I'm going to do that now. It's kind of a standalone chapter and incorporates some of the stuff we've done before. It's very simple. If you want to know more information about how this works, it is in my notes, but you don't need that for the test or the homework. So I'm going to go through the basics of what you need right now. And if you would like more information about it, feel free to check out the notes on the Google Drive for 8.5, or feel free to ask me and I would be more than happy to go more in depth about it. But what we're going to be talking about is something called a normal probability plot. What this is a graph, and it's going to plot each of the x values in your data set against what their z value would be. So remember, for data points, we're not looking at sample means, we're not looking at sample proportions here. We are just looking at the data points that we use. If you remember back to when we did this, the z transformation for each data point was this. So it was the data point minus the mean divided by the standard deviation. This z transformation took us from a normal distribution that had a mean mu and a standard deviation of sigma, whatever those values might be, and it pulls us back to our standard normal distribution. So this z transformation will go from a normal distribution with a random mean and standard deviation to that standard normal distribution that has a mean of 0 and a standard deviation of 1. So that's why we like to use it. But what this normal probability plot does is it's going to give you this graph where it's going to plot each of the x values on that x-axis. So these are going to be your data points, okay, for your whole population or sample, depending on what you are looking at. And then on the y-axis, these are going to be your z values, your z-scores. Okay, so for each x value, you're going to subtract the mean and divide by the standard deviation and find its z-score. And then you are going to plot that x value against the value that you got for its z-score. Okay. Now, if you were to use this, the reason behind using this would be that you want to see if this data set has a normal distribution. We tend to only use this when you are looking at most 30 data points. We don't tend to use it if you are looking at more than 30 data points, just because it gets to be a lot of points and it just gets kind of confusing looking at these on a line. So we tend to only use this normal probability plot to tell if something has a normal distribution if you have at most 30 data points. Okay, how can we tell if this thing has a normal distribution? So how can I tell that my data points x have a normal distribution? Well, what you should find when you plot this is that your data points against their z values should lie roughly in a straight line. Okay, you may have a point or so that are slightly off of that line, but you should find that most of them will fall on a direct straight line. Okay, if that is the case, so if the points fall on a straight line, that means the data points X have a normal distribution. Okay. We like to use this because normally we know that something has a normal distribution if we plot the data points where we have on the x-axis is the data points X, and the y-axis tells us the frequency of each of these data points. What we tend to do is we plot that and we find if it's got this bell-shaped curve, that symmetric shape. Problem is, when you have less than 30 data points, that thing might be kind of off because you don't really have enough data there to really give you that smooth bell-shaped curve. So when we have less than 30 data points, this is the best way to tell if it has a normal distribution. Okay, if you have more than 30 data points, so for n greater than 30, plot the histogram where you are plotting the x values against their frequency, and you should get the bell-shaped curve. Okay, so there's two ways to tell if these data points have a normal distribution. Either if you have less than 30 data points, you plot their normal probability plot and that lies in a straight line, or if you've got more than 30 data points, plot a histogram where you've got the x values against their frequency and it should follow a bell-shaped curve. Coming back to this normal probability plot, something I should mention is when you've got this normal probability plot that looks like this, okay, if you have more than one outlier, so if you have more than one point that lies way off of this line, it is considered to not have a normal distribution. So in order for this thing to have a normal distribution, we say it should lie on the line. You are allowed at most one outlier. So should have no more than one outlier to be considered normal. Okay. If you have two or more outliers, then this thing would not have a normal distribution. Okay, so that's a good thing to remember when you see these. Just as a quick side note here, if you do want to know how they plot these, I have actually put the instructions on my notes. There is a 4-step process as to how they actually go about plotting these normal probability plots. So if you would like more information on it, then please go ahead and look there. They do have that step-by-step process. You don't actually need to know this for this class. I just wanted you to know what you are looking for a normal probability plot, okay? So keep that in mind. If you did want to plot this on your calculator, there is a way to do it. If you go ahead and put your list of data into list 1, list 2, list 3, wherever you want in your calculator, put your data points as a list in your calculator. If you then go to second and the Y equals button right on the top left hand corner, so second and stat plot, go to plot 1 and make sure it's turned on and all the others are turned off. Under type, right at the end, is something that looks like a scatter plot. That thing is actually a normal probability plot. So whichever list you put your data into, make that your data list. And the data axis is going to be X. That's the axis that holds our data points. Then it will put the Z value for each of our data points on the Y axis. Okay, so make sure your data axis is X and that your data list is whichever list you put your data points into. And the type is the very last graph that you could possibly have. That is a normal probability plot. It will then plot this thing for you if you go to zoom right in the middle at the top go to zoom and number 9. It will plot this thing for you, and you can see if this thing lies on a line. Okay, so that is a good way to make a normal probability plot. Remember, z values are going to give you something that looks kind of symmetric. So you're always going to be crossing that axis, that 0, okay? Because 0 is going to be in the middle. Think about the z values. The mean is always 0. So you're going to have 0 in the middle, and then you're going to have some positive values and some negative values of z. Okay, think about it when we do our normal curve, our bell-shaped curve, okay? 0 is the middle value, and then you have z values either side, okay? So 0 is going to be in the middle. So your x-axis is going to cross, y is equal to 0, and your data points will go both positive and negative, but should lie on a line. Okay, so that is a good way to check it. Okay, keep that in mind. If you've got any questions, please let me know, and I will see you in the next video.